Good morning and good afternoon to you all. You know the routine already. I'm pleased to welcome you to this webinar on energy reduction in your industrial environment. I'm Patrick Bekel, Commercial Director of VONK, and most of you have seen him before. For the others, I would like to introduce you to Dave Oosterholt. Dave studied in the Netherlands at the Technical University of Twente, where he obtained his master's degree in chemical engineering. Dave is Senior Consultant with VONK, and he's a specialist in the energy transition. I hope you all enjoy the webinar, and good luck, Dave.
Thank you very much, Patrick, for introducing me. Welcome everyone to this webinar, a new one in the VONK series of webinars. In the next 30 minutes, I'd like to tell you more about the latest development, how to reduce energy and how to reduce your CO2 emissions at your industrial facilities. After the webinar, there will be room for questions. You can leave your questions in the chat box, which you can see at the right of your screen. If you can't see it yet, push the 3 black dots and the chat screen will appear. So I'll dive into your questions after my presentation, which will take about 25-30 minutes. So this webinar is about how to reduce energy consumption and CO2 emissions at your industrial facilities. But this is related to electrical power generation and consumption. I've prepared a short agenda to give the presentation some more construction. I will first introduce VONK shortly, then I will dive into the scope of the webinar, what will it be about and what will it not be about. Then the route, how to reduce energy consumption and CO2 emission, which route to follow, and on that route, which technologies and methods can help you, and also combining smart energy management with process optimization, process control. Then I will recap, and then there will be room for questions. VONK, who is VONK? VONK already exists more than 80 years. It's actually been founded by Mr. VONK himself. We have been part of different companies in the past. We had different names, but at the moment we are VONK. We are an international solution provider of power supply, process control, and power conversion solutions for complex energy transition related challenges. And in this webinar, especially the power management systems, the control and automation systems, and the drive solutions will come back. Let's skip to the scope of the webinar. What will it be about? What will I bring you in the next half hour? Mainly 2 messages. The roadmap which you can follow, the route to follow to save energy and to reduce your CO2 emissions. Which methods and technologies are available for you on that route. And the methods and technologies I will dive further into are energy storage, recuperation of energy, efficiency of motor drive systems, which processes can be electrified at your industrial installations, the integrations of renewables, and last but not least, the smart combinations of power management and process control. Of course, illustrated with different use cases off-grid as well as on-grid. Let's look at this route first. It looks trivial, of course, many developments, many implementations, there's a route to follow, and also for this one. But if you really want to save on energy and CO2 emissions, and reduce your CO2 emissions at your industrial facilities, it's important to follow a phased approach and take it step by step. Also, do not make those steps too large. Then, if you would do that, then it could happen what you see in the picture at the right, that you will never reach your goals. It's also important to follow, back please, yes, a holistic approach, where you combine smart energy management with process optimization and combine different technologies and methods. Following the route, it's important to have a team working on it which is multidisciplinary, consisting of engineers and experts out of the electrical instrumentation area, but also control and automation, and last but not least, also process control and engineering. So on this route, which methods and technologies could support you in reaching your goals for CO2 emissions reduction and energy saving? I will dive deeper into energy storage systems, how they can help you on that route, energy recuperation, electrical motors and drive systems, electrification of industrial processes, and integration of renewables. Let's first look at energy storage systems. Before I will show you how these can be of use for you to reach your goals. First, what it actually is. Many of you, of course, already heard about energy storage systems. There are many different forms of storage systems. They are basically there to store your energy temporarily, can be long-term, can be short-term, in order not to lose the energy. Yeah, if you have excess produced renewables, for example, you can store them instead of dumping it. You can also store recuperated energy. I will show you in some use cases later. It's also a way to store the energy for the moment that you need it again, because not always the power that's available is being needed directly at that moment. So you can store it for later. This can also, of course, be of financial benefit, but that is another subject for another webinar, maybe. And you can use it to shave off your peak loads in your industrial processes. And in this graph, you see the different groups of energy storage systems. There are battery systems that are mainly there for the short-term storage up to a certain capacity and rated power. So the lithium-ion is a famous one of that one. Then you have the upcoming redox flow batteries. I'll show you a bit later what those are. And then for the very long term or the longer term storage, you think of weeks and seasonal on a yearly basis even, you can store it in the form of hydrogen. Of course, you can use hydrogen also for short-term storage, but it's also very suitable for the longer term. And also compressed air and hydropower. In this webinar, I will focus on the storage of hydrogen and in batteries. Looking at the battery storage systems, there are also different forms. Most can be divided in two groups, basically. The ones that are called solid-state batteries. We all know the lithium-ion, and of course the lead acids and the nickel-cadmium kind of batteries you see in the picture. They're mostly stacked in cells, in stacks of cells, and can be containerized, for example. And there's also the redox flow batteries. They can store the energy longer. However, the energy density is quite somewhat lower. In the bottom left picture, you see, for example, 8 40-foot containers that is used to store 4 megawatt hours of energy. So the footprint there is quite a lot larger. It's also because the electrolytes are in the liquid form. When you look at hydrogen can be stored in different ways. The advantage of storing hydrogen is, as I said before, it's very flexible in the duration. You can store it how long actually as you want. You can store it also in different quantities, basically limitless if you have more tanks and vessels. They are stored in, the hydrogen can be stored in the gaseous form, which is a well-known method to store it in high-pressure cylinders and vessels. Can go up to 800 bars. In the liquid form, you see that also coming up, cryogenic. Then you need to cool it down to very low temperatures, minus 250 degrees C. This will be at atmospheric pressure. And an upcoming technology is also in the solid state, mostly done by absorption in metal hydrates. The hydrogen is not there, of course, just by itself. You have to produce it first from power, from electricity, splitting the water into hydrogen and oxygen. And this is done by an electrolyzer, as you can see in the picture at the right. And back, when you produce out of hydrogen electricity, there's a fuel cell needed for that. Let's look at an example of such a hydrogen storage unit. In this case, this is a bi-directional unit. It's an upcoming technology. More companies are working on this. So that means actually you can transfer your power into hydrogen and at the later stage transfer it back into electricity when needed. So it's a bi-directional unit. And the nice thing about this, as you can see in the graph, the green bars show when the hydrogen production is highest. And you can see that in the summer months, for example, if you have renewable power generation from solar cells, they produce a lot more power mostly, or they can produce more power than you need at that moment, and you can store that in the form of hydrogen for later. So your hydrogen storage, the yellow line, will gradually over the summer and autumn months build up that you can then use, for example, in the winter. So this is a nice development you can use for different situations, also in industrial facilities, also, for example, offshore platforms for the seasonal storage. They're currently quite small still, 5 kilowatt range, maybe 10, but they are actually in development of going up to quite a lot larger powers already of more than 100 kilowatts. You can also combine battery energy storage systems with hydrogen storage. This is a schematic showing this. So where you can have the battery energy storage systems on the left and the hydrogen storage systems on the right. Of course, the electricity can come from the grid, but also from the renewables as wind energy and solar energy. And the consumers at the end, they can be the grid connected. It can also be your factory or your industrial facility. So the battery energy storage systems, they are mostly then used for short-term storage. For example, in situations where you have in the grid a net congestion, you can react very fast on that, or to help you with your peak loads, to shaving the peak loads, rather than putting a gas turbine to a higher power. That's an example for battery energy storage systems. I will show you in some use cases later. The hydrogen storage systems is more for the longer term, as I said, and you can use that for seasonal storage. But of course, you can also use the hydrogen you produce, not for later to transfer back to power, but also for different purposes in your industrial facilities. For example, you can have your forklifts run on it, or maybe some trucks, lorries. There are different ways to reuse hydrogen, of course. So it's very flexible. Similar situation. This is a slide I just would like to show you that you can also, instead of an AC-based system, have a DC-based system. And this is an upcoming technology for the quite large applications. So that's what we want to keep an eye on for the near future. Another way to regenerate energy, recuperate in this case, and so it's not wasted, is energy recuperation. You'll see this already being applied in actions at your industrial site. For example, hoisting, the cranes, in the downward movement of the crane, when it needs to brake again, it can regenerate the energy for the next action for hoisting up again. For example, in a flywheel type of energy storage system. We together with a light rail company working actually on a very sophisticated system where we power, in this case, the light rails, the trams and the metros, light rail application, not only to power the metro, but also to regenerate the energy from braking and put it back into the grid. As you can see in the picture, so far this energy is being actually dumped basically, because you have to get rid of it in the so-called resistor banks at the top of the trains. So directly, again, to save energy, you can use recuperation. The next method of saving energy in your industrial installations is electrical motor drive systems. When you have in your processes multiple systems turning around, like in drying bins or extruders or centrifuges, and these are being driven by drive systems and electrical motors, there is a possibility to adapt the electrical parameters in such a way that the overall efficiency will improve. An example we have done for customers at an industrial site where we have multiple centrifuges and our drive systems installed is an adaptation in the drive system supplying power to the electrical motors for these centrifuges, and we have applied a very specific technology to make those centrifuges run on the energetic sweet spot. And in this case, in one of the cases, the customer for one of their factories saved more than 8 gigawatt hour of energy per year. So that is quite substantial. So looking at those motor drive systems, there can be quite a lot to gain there as well. Electrification, we've all heard about it. There are different processes now in industry and also other industries and markets where processes are being electrified. And also this is the case in industry. Yes, that can save energy as well, but the main driver is here, of course, the reduction of CO2 emissions, because you replace your fossil fuel heaters, for example, by electric heaters, or you replace your fossil fuel engines by electrical motors. I will show you an example where this is actually being considered at the moment. If you go to the next slide, I will see that we'll show you that there are more than, there are actually thousands of onshore gas wells in this part of the world, where a gas water mixture is being pumped up from the ground up. And this is done by a hydraulic package that is currently being driven by a combustion engine, which is basically a car engine. Then the gas water mixture is being separated into gas and water, but part of that gas is used to fire the combustion engine to drive the hydraulic package. This is not the ideal situation though. We have, of course, the emissions. We have next to CO2 and CO emissions, also the infamous SOx and NOx emissions. We have gas production losses because you use part of your produced gas to run the combustion engine. And we have also intensive maintenance. Teams are going there every day to keep maintaining these combustion engines. Not related to the subject of this seminar, but noise pollution is also an issue here. This can all be solved by a quite simple solution, is replacing the combustion engine by an electrical motor. Next to being quiet, of course, you don't have the emissions anymore. You don't need any of the produced gas, and the maintenance is very limited. And you can drive those electrical motors even with renewable generated energy. In this case, a little solar park next to it with a battery energy storage system, so also to come through the night. And you have a total green system, saving energy all over as well, but mainly also reducing your CO2 emissions. This was an example of electrification. So how can we combine all these methods and technologies even in a smarter way by combining smart energy management and process optimization, process controls? I'll show you in the next few slides. Here we have an example. It's a rather small off-grid installation. The plant needs 50 kilowatts average of load. We have a diesel generator in place and a backup diesel generator. However, in this situation, it's not ideal because the diesel generator should run at least at 70% of its maximum load of 120 kilowatts, or 100 kilowatts in this case. So this, and it only runs at 50 kilowatts. So that's not ideal. So what is traditionally done is to put a load bank in place that's taking part of the energy, but that energy is actually being dumped. The diesel generator will be above the 70% load, so it will be in its sweet spot, but you lose quite a lot of energy in your load bank. Also, in this case, you need quite a lot of maintenance of your diesel generator. Let's say every 1,000 hours, 42 days. You need to go there, so that is also taking quite a lot of CO2. And you need to refill your diesel tank quite regularly. This can already be solved quite quickly, or improved at least, by introducing a battery energy storage system. Your diesel will not run all the time, maybe about half of the time, and your battery energy storage system is taking care of the rest of the time for the load. And in this case, your frequency of maintenance is even reduced by 2, so you only have to go there half the time. Also, the same is for refilling. So, and your diesel generator is also running less, so that will reduce CO2, and also going there less than before also will save or reduce your CO2 emissions. You can improve the situation even further by introducing renewables. So, for example, a solar park or some smaller wind turbines or larger wind turbines. If you put that into the mix, then your diesel generator more or less acts as a backup only, and only needs to be serviced once a year. The tank needs to be refilled once a year. That's quite a large improvement. Similar case like this we have already applied on offshore wind, no, not offshore wind, offshore oil and gas platforms, I should say. In this case for Shell ONEgas. We call this a hybrid power system, energy being generated by the solar panels and stored in batteries, as you can see at the bottom right picture. So this is already running for many years, and actually the diesel hardly comes on to act as a backup. A larger example, the load is quite a lot higher here. The industrial facility needs 20 megawatts of energy. This is now being supplied by 2 gas turbines and 2 dual fuel turbines. 3 of them are running. However, the load is not always 20 megawatt. There will be peaks. And in this case, you need the 3 generators to cover those peaks, because 2 alone, which only comes up to maximum 22 megawatts, as you can see in the graph at the right, will not be enough. So you need the 3rd one. It's not an ideal situation. Okay, your load is above the 40% that the turbine should run on, but it's not ideal. And the higher the load is, also the efficiency will increase. So how can this situation be improved? So this is the peak that you want to take care of, and this can be done by introducing again a battery energy storage system. And that will shave off your peak, and the nice result of it is that you do not need the 3 turbines anymore, but only 2. And they will run at a higher load, therefore run at a higher efficiency. This will already reduce the CO2 emissions, taking out of operation the 3rd one. Also, of course, direct CO2 emissions, energy savings. So this is a lot better situation for, in this case, a larger off-grid installation. The case we are working on at the moment is similar. Just I wanted to show you because it's actually also a practical case. 1 gas turbine, 2 gas engines, but at this moment the gas turbine is running very, very poorly. It's not an ideal situation. So how can this be solved? Again, by introducing a battery energy storage system. You can take the gas turbine out of operation. Also, you do not need the diesel engine anymore for the backup, because you already have the battery energy storage system in place for that. And the battery energy storage system will cover your peak loads. So it acts as a peak shaver, or also called a spinning reserve. This is a nice example. The results again are less fuel consumption, saving energy, reduced CO2 emissions, and less overall maintenance. Last but not least, smarter power management. Very important. Power management has always been done, of course, but in most cases this is limited to the electrical parameters. Load sharing and balancing between generators, approval for starting up certain consumers at your plant, acting based on the spinning reserve available, the reserve in your generators, and the automatic starting and stopping of generator, and also load shedding. Next to that, we have process control. Industrial installation often contain kind of what you could call energy buffers. You have volumes in storage or buffer tanks, and these volumes need to be kept at certain levels, a minimum and a maximum. But there is room between it. That's allowable. There's temperature of the process. You have to keep the pressure, the temperature at certain levels. And there's pressures in your instrument air system, for example, or in hydraulic accumulators. And they could act as buffers. It all depends on timing. Timing is very important here. I can illustrate this maybe by these 2 figures, 2 pictures. The top left shows actually power generation is going like mad. There's power available, but at the process side, they actually do not need it at that very moment. So there's no communication between process control and your power management system. There's, let's say, a virtual wall in between. This is not an ideal situation, because when the power is available, you could use it at that moment already to bring that volume to a higher level, or to the pressure to a higher level when the power is available. On the other hand, the picture on the bottom right is that the process is actually turning it on, whilst the power cannot cope with it at that moment because it's already at its max. That is the situation I just said. If we use the power when available and let these two systems communicate with each other, there's a lot to gain. So that's what's said here in this slide. Using the energy buffers in your process control, but that also requires a multidisciplinary and holistic approach again, integrating the electrical engineering with your process optimization or process automation. But the synergy between your power management system and your process control system will then improve your overall balance between supply and demand, and that increases overall system energy, with the end effect again to reduce your energy consumption and also your CO2 emissions. This already brings me to the recap of this webinar. In the last 20-25 minutes, I've tried to tell you that when you would like to reach your energy saving and CO2 emission goals, and these get more and more stringent also by regulation, it's best to follow a phased and holistic approach, using a multidisciplinary team for this. They then make smart use of energy management, but as well as process optimization and process control. Let these two communicate with each other, and let them use a combination of different technologies, of which energy storage, recuperation, more efficient electrical motors and drive systems, electrifications, and integration of renewables are good examples to follow. I thank you very much for your attention. I hope this webinar brought you what you expected from it. There's many ways to save on energy, to reduce your CO2 emissions. VONK has done it already in many industries, in many different projects, and of course, we are more than willing to support you in this. Let's have a look at the questions. I see there are not that many questions. I see that there's one at the point that the application of a battery energy storage system for peak shaving. So there's a reduction of peak consumption, for example, caused by starting of big electrical motors. So only applicable for off-grid situations. The answer to that is no. It also applies for on-grid situations, but then more in terms of reducing the maximum supply value in your contract, because you all have to secure a contract with your energy supplier, and by having smart solutions like energy storage systems in your factory, in your plant, you can maybe gain with that you do not have to have such a large consumer contract with your energy supplier, with your grid operator. Another question I got is if I could provide some numbers on compressed air storage. Question from Arthur Hartl. At the moment, I'm more than willing to give you the answers. I don't have the answers at the very moment, but we could certainly help you there. Tests are going on to look at those compressed air systems, and we know you, so we will come back to you. It also differs per application, basically. There are different ways, though, to store energy. Also offshore, quite a recent technology there is to store energy in a kind of inflatable systems at the sea, at the bottom of the sea. They start to use this now to store energy from, for example, from large wind turbines. There is also tests going on for the compressed air systems, as I have informed correctly, to store those energy in depleted in the salt caverns. So that's another technology, another innovation we are following as well. I think that concludes the webinar. So If you have more questions, of course, just be our guest and email them to us. We're always willing to help you. And look out for the next webinar, which we will be organizing probably in the second quarter of this year. We will have one each quarter. Thank you again for your attention. Have a great day and see you the next time.